Hello and welcome back to Grokking Graph Algorithms and Analytics. Today we're going to be covering some definitions. A node is the fundamental unit that forms graphs. For most algorithms, it is considered indivisible. This could include something like cities or computers or even processes. And edges are the sort of other main component of a graph. And what these are is sometimes they're ordered, sometimes they're unordered. So we do want to put a nod to that in the definition. But it's essentially just pairs of nodes. For example, you could have cities and the streets that connect them. Let's call it cities and the highways that connect them. Or you could have computers and their network connections. Or you could have, for example, processes and ordered pairs of processes indicating dependency. So we want to represent graphs in ways that lend themselves to computer algorithms, and hand-drawn pictures definitely isn't one of those. Let's consider the matrix representation, where each row and column corresponds to one of the nodes. So we have A, B, C, and D, and we also have rows that correspond to that. And then the entries of the matrix correspond to the number of connecting edges between vertexes. So, for example, between A and B, we have one vertex. So we can put a 1 here. And since this is an undirected graph, we can put a 1 here as well, because there's one edge between B and A. Similarly, between B and C, there's one edge. So we can put a 1 here and a 1 here. Well, what about on the diagonal? If we look, we see that there's no bridge connecting A to itself. So in the AA entry, we put a 0. Similarly for the rest of the diagonals. Sometimes a graph will have an edge connecting a node to itself, and so the numbers on the diagonal might not always be 0. Let's look at another example, A and C. There's no edge connecting the nodes A and C, so we can put a 0 on that entry as well. And there's 2 edges connecting A and D, so we can put we put the number 2 here, representing the number of edges connecting those 2 nodes. Why don't you go ahead and pause the video and see if you can fill out the rest of the matrix. Okay, let's go ahead and fill out the rest of the matrix. If we look at this entry right here, we see that between B and D, there's exactly one edge. So we put a 1 in that component. And since this graph is undirected, this matrix will be symmetric, and we put a 1 there as well. Between C and D, there are 2 edges. Between A and C, there's 0 edges, just like between C and A. And between A and D, there are 2 edges. Let's go ahead and just rewrite this a little bit nicer. And this is our matrix representation of our graph. Let's consider the edge representation next. The thing about graphs and their representations is that different representations serve different purposes. Adjacency matrix is a really useful way to store graph information and transmit it and visualize it in a way. Another way to look at a graph is with an edge list. and that's literally just a list of pairs of vertices. In a directed graph, the pairs would be ordered. Since this particular graph is not directed, the list or the pairs are unordered. So it would look something like this. There is the connection between A and B, and we don't put the connection between B and A. And it's a set, so I'm going to put a little curly bracket over here. Between A and B, we have that connection. There's also a connection between B and C. Between C and D, there are two connections. Go ahead and pause the video and see if you can fill out the rest of this edge list. Okay, let's keep filling out this edge list. We just wrote down the edges for C to D. Let's write down the edges for D to A. Since there's two of them, we write it twice. And there's also an edge from D to B. Let's see. So this is an undirected graph, and there are 7 edges, and we see that we have 7 pairs. So we know that we're done. The last way I'm going to discuss to define a graph is with an adjacency map, or in Python, an adjacency dictionary. Recall, in Python, dictionaries are defined with curly brackets, and the key, in this case, is going to be a node name. And the value will be an unordered set of the nodes that A is connected to. So that would be B and D. And we see that it is connected to D twice. So we'll just put D down there twice. Similarly, we can write the key value pair for B as being A, D, and C. Go ahead and pause the video and see if you can write down the key value pairs for C and D. Okay, let's finish writing out the adjacency dictionary. We see that C is connected to B and D twice. So write B, D, and D. And lastly, we see that D is connected to A twice, and it's also connected to C twice, and it's connected to B one time. So those are the 3 different representations. We have matrix, we have edge list, and we have adjacency list. Let's go ahead and finish this section with some terminology. A label is one member from a set of other members that indicate group membership. So, for example, we could have a graph that represents a network of computers, and some of those computers would be labeled as servers, and some would be labeled as clients. A path is an ordered sequence of vertices and their edges. A path is an ordered sequence of nodes. For example, if we revisit the Bridges of Königsberg problem, and we take a walk from A to B, then B to C, then let's say C to D, and then back to B, we can say that that path is the edges AB, BC, CD, and then DB. Properties are key value pairs belonging to either a node or an edge that indicate some kind of information within that node or edge. If we revisit the Bridges of Königsberg problem, recall we labeled each landmass with a letter, A, B, C, or D. So the property here is the name, and in this case, it's A. Lastly, a subgraph is a graph of another graph that's formed from a subset of the vertices and edges. For example, if we look at the Bridges of Königsberg problem, we can see that if we take just the graph, or just the node D, B, and C, and connect them thusly, that's one subgraph. We can also include the edges between D and C, and that's a different subgraph. It may seem kind of weird to bring up the terminology or the term subgraph, but it's important when we're discussing things beyond pure graph theory, right? Remember, this is about analytics and algorithms around graphs, and subgraphs really come in useful when we're dealing with databases, whereas whole graphs are more centered around algorithms, and analytics sort of falls somewhere in between the two.